Good morning, everybody, and welcome back to Math 105. So before we get started, I thought I'd talk a little bit about the nature of why I'm kind of moving online the way I am. I decided not to make like all classes kind of synchronous through Zoom because I don't want to stress you all out too much right now. I'm trying to avoid stressing students out, and I think just having these sort of pre-recorded lectures is kind of the easiest for you all, and honestly the easiest for me. But we'll still have these one day a week, currently scheduled to be Wednesday. Might end up being Friday, depending on how things go. Having these like one day a week sessions where we'll meet up by Zoom, which I'll be getting to you about in the next couple days. Anywho, plan for today is we're going to finish Standard 16 by doing this proposition at the back where we talk about how can you double a square. And then start Standard 17, where we start talking about how did the Greeks and other geometers have trouble doing some constructions that were similar in nature to the ones we talked about in Standard 16. I've got my usual office hours today. Don't forget, office hours will work the same way they have all semester over Zoom. My office hours today and Wednesday are 10 o'clock and at 2. Tomorrow morning, I usually have an office hour from 10 to 11:30. This week, it's only going to be from 10 to 10:50 because of a department meeting, unfortunately, at 11. And 1:30 to 2:30. And as far as homework goes, there will be a Standard 16 quiz that's going to be due Wednesday evening. So last time, if you recall on Friday, we talked about last Wednesday, Friday was the exam. Last Wednesday, we talked about Proposition 11, which says you can always draw a straight line at right angles to a given straight line from any given point on it. Meaning, if I have this line from A to B, and if C is any point on the line, according to this proposition, I should be able to draw a straight line coming out of the point C that is perpendicular to the original line AB where we started. And that's going to be important for today's constructions. So today, I want to do kind of a new proposition that was not actually something Euclid proved in the Elements, hence why I called it proposition triple question mark. It's not one of Euclid's proofs, but this is kind of a proof that I think would be similar to what Euclid would do if he were to, if he had tried to prove this within the Elements. Because if you recall, the question about how do you double a square was one that came up in Plato's Meno last week. As sort of this philosophical exercise related to Socrates proposed, related to anamnesis. And Socrates kind of showed a solution within that story, but we're going to try and do that formally here today using proposition number 11. So let's see if we can prove this. Given this square, ABCD, can we find a new square whose area is double the area of the original square? So first of all, I'm going to let square ABCD be described. With all side lengths equal to 1. So I drew out a square here, ABCD, and we're going to assume all the side lengths of this square are just 1 unit apiece. So what would the area of this square then be? Well, area of the square is going to be 1 times 1, which is just 1. So thus, with area 1. 1 what, Dr. Gerstle, you might be asking? Well, the units don't really matter. It could be 1 foot, 1 meter, 1 mile, 1 light year. Doesn't really matter. We just need to find a square that's going to have an area of 2 of the same unit. So we're going to, first of all, let the straight line AC be joined. which is going to be something that postulate 1 allows us to do. Draw a straight line going from A to C. You may remember from Socrates' construction that the way that given a square, the way he doubled it was to actually use the diagonal of the square, and that's what we're going to be doing. So we're going to let AC be joined. From A, we're going to let the line EF be described perpendicular, how do I spell this? Perpendicular to AC. So in other words, I'm going to take at the point A, I'm going to draw a new line that intersects AC here at a right angle. And let's see, this point down here I'll call E, this point way up here I'll call F. And we want this to be a right angle right here, from the line EF to the line AC. So Dr. Gerstel, you might be asking, what proposition or postulate allows us to draw this line EF that's at a right angle to AC like this? Well, it's actually going to be proposition number 11. This proposition from last Friday. And that's why I wanted to prove that proposition in this packet, is because being able to draw perpendicular lines is something that's necessary in this proof of doubling a square. So we have this big line here, EF, that is perpendicular to AC. And now I'm going to do the same thing at C. I'm going to draw a straight line from a point here, G, to, let's say, a point way out here, which I'll call H. And that intersects C at a right angle. And to do that, we can use the same proposition number 11 that we used to construct the line EF, where both EF and GH are going to be perpendicular to the line AC, but perpendicular at different points, at A versus at C, respectively. So from C, let the line GH be described that is perpendicular to AC. And this again is going to come from proposition, I have to write that down here, it's going to come from proposition number 11. So now we have two lines where both GH and EF are going to be lines on which we draw two of the sides of our square. So now, do you notice EF and GH can't themselves be the sides of the new square we're going to construct because EF and GH are too far apart. So the next thing we're going to need to do is we're going to need to pick points on the line EF and on the line GH, let's just be a bit more G-like, so that A to this new point we're going to draw right here, we'll call that point I, and the distance from C to this point right here, which we'll call point J, we want to construct AI and CJ, as well as AC, to be the same length as AC. So in other words, we're going to pick a point I on this long line here, and a point J on this long line here, such that the distance from A to I, the distance from C to J, are both going to be equal to the distance from A to C. So let's write that. On AF, we're going to let AI be cut off equal to AC. And on the line CH, we're going to let C to J be cut off equal in length to AC as well. So how do we know we can do this? How do we know we can pick points J and I on this line such that the length of the line from A to I is equal to the length of the line from A to C, and similar with CJ? Well, this is the same proposition that we've used a lot of times now, the one that says if you have a longer line, say from A to F, and a shorter line, say from A to C, we can cut A to F off at a point, in this case I, such that what's left after we cut off the excess from A to I is equal in length to the line from A to C. Let's move this a bit more over here. What proposition was it that allowed us to do that? Well, it turned out that's our good old friend, proposition 3. One that's shown up in a lot of different proofs now. It even showed up as part of our proof of proposition number 11, if you recall. So now, we're going to let the straight line IJ be joined. Again, using postulate number 1. Boom, like that. And here's going to be the square I claim has double the area of the original square. I claim the square going from A to C to J to I back to A. This square here is going to have an area that's equal to double the original area of the square A, B, C, D. So we let IJ be joined, and then I'm going to claim that ACJI forms a square. So here's a question I have for you. I'm saying that ACJI forms a square. How do I know that IJ has to have the same length as AC? Or for that matter, how do I know that these two angles, angle AIJ and angle CJI, how do I know that those form right angles? I'm not going to say. That's actually going to be, you can actually use later propositions in Euclid's Elements to say IJ has to be the same length as AC, and AIJ and CJI have to both be right angles. And you can actually use that by means of the parallel postulate, which we haven't used up until this point in the semester. But I'm going to leave those details off. And just because I don't want to spend another 2 or 3 classes getting those details down. So ACJI forms a square. It will have to be the case. And now we can say that since the triangle ABC is a right triangle, ABC, so in other words, since this triangle is a right triangle, we can say that the length of the segment AC, if we were to square it, should be equal to the length of AB squared plus the length of BC quantity squared. So in other words, this length, the diagonal of the original triangle, the length of that squared should be equal to length of AB squared plus the length of BC squared. Why is that? That's not a proposition we've proven yet. Well, you might recognize this one as being from the Pythagorean Theorem, which is, in Euclid's Elements, proposition 47. The one that says if you have a right triangle, then the length of the hypotenuse squared is equal to the sum of the length of the other two sides squared. So this side squared plus this side squared is equal to the hypotenuse's length squared. Well, what else do we know about the length of AC squared? It's length of AB squared plus the length of BC quantity squared. But we know exactly what the length of AB and the length of BC are. AB and BC both have length 1. That was one of our starting assumptions. That all the sides of the original square, including from A to B and from B to C, have to be length 1. So we can actually fill this in and say this is going to be 1 squared plus 1 squared, which if we add together is just going to be 1 plus 1, or 2. So we know that the length of AC, quantity squared, is going to be equal to 2. 2 units where we haven't, we haven't specified what our units actually are. And here, we're going to use the fact that we constructed a square then, to say a couple of things. We can then say that, but, since the length of AC is equal to the length of CJ, why is that? Length of AC equal to the length of CJ. Well, it's because AC and CJ are both sides of the same square. Meaning AC and CJ, since they're both sides in the same square, have to be the same length because any two sides of a square always have the same length. So now we can say that since the length of AC is equal to the length of CJ, now we can take the area of the square ACJI. This is the area of this new square I constructed from A to C to J to I and back. Well, by definition, that should be equal to the length of AC times the length of CJ. You just take width times height of a square to find its area. So just take any two sides, multiply them together. That should give you the area of your square. But the length of AC times the length of CJ, using the fact that the length of AC and the length of CJ are the same, it's just going to be the length of AC times the length of AC, which is equal to the length of AC quantity squared. We're taking the length of AC times the length of AC. But what is the length of AC squared? We already said over here that's going to be equal to 2. Therefore, this new square ACJI is going to be a square whose area is double the area of the original square. So just a quick sentence to wrap that up. We're going to say, thus, ACJI is a square whose area is double the area of our original square ABC. And QED, thus it is proved. We showed that starting with an original square ABCD, we can construct a new square ACJI whose area is double the area of the original square. Okay, so that's going to do it for Standard 16. But before I pull away from this video, I'd also like to start talking a little bit about Standard 17 and what we're going to be looking at in that standard. Standard 17 is not going to be a very long one. I think this one we can kind of get through in a like a class and a half, 2 classes. So Standard 17, so if you flip to the new packet, is going to be one where we ask questions of, instead of, is it possible to construct some things, we're going to ask the questions of, is it not possible to construct certain types of geometric objects from Euclid's postulates. And so in particular, in Standard 17, I'm going to flip to the second page in the packet. we're going to look at 3 classical problems of geometry from the time of Euclid. The first is a question of, can we trisect angles? The second is going to be the question of, can we double a cube in the same way that we just doubled a square? And the third is squaring a circle. So these were 3 sorts of constructions. We'll talk about each one in detail here in a minute. But these were 3 things that the Greeks wanted to be able to construct. We talked about how to, for instance, double a square. Given some square, how can we make a new square whose area is double the area of the original square? The Greeks were also interested in, can you always do that with a cube, say? Meaning, given a cube, can you find a new cube whose area, or not whose area, whose volume is double the volume of the original cube? And we can bisect angles. Euclid had that in the elements as proposition 9. Can we also trisect an angle, which is a similar sort of question, but one that Euclid didn't include a method for how to do in the elements. And so the question with these 3 classical problems that mathematicians for thousands of years were interested in trying to work out, can you do these 3 things using a recipe coming out of Euclid's postulates, Euclid's common notions, and the propositions. So Euclid didn't describe how to do any of these in the elements. And geometers, for a long time, struggled with showing how to do these things using Euclid's tools. Struggled with showing how you can do these 3 constructions only using Euclid's postulates and the common notions. Get rid of this. So in other words, geometers, these chalks flying apart on me. Wanted to know, can you use just a straight edge and compass to find a way to, say, trisect an angle, double a cube, or to square a circle? Because if you remember, Euclid's postulates were based around things that you can do with the straight edge and compass, at least the first 3. And so, geometers for thousands of years were wondering, can we similarly use straight edge and compass constructions? In other words, right as a proof using Euclid's postulates and common notions, can we figure out a way to do these 3 procedures in similar ways to how can we do things like bisect an angle or double a square? And now, what I would like to do is to talk very briefly about each one of these 3 constructions, just so we can get a sense of what does that mean? What does each one of these mean? So the first one we're going to talk about is trisecting an angle. So we already talked about what it means to bisect an angle. What it meant to bisect an angle was given an angle, BAC like this, can we find a point in between B and C, D, such that angle BAD and DAC end up being equal to each other? That was the question from last packet in Proposition 9 of how can we bisect an angle. And Euclid showed that just using his propositions, that's something that you could do. You could draw equilateral triangles, use a straight edge and compass, do a bunch of different things that would eventually allow you to bisect an angle, cutting an angle in half. So if that's what it means to bisect an angle, what do you think it might mean to trisect an angle? If bisecting, bi meaning two, means to cut an angle into two equal pieces, trisecting an angle is going to refer to cutting an angle into three equally sized pieces. So in other words, finding two different points between B and C, let's say a point D here and a point E here, such that all three of these angles end up being equal to each other. So the question the Greeks were interested in is, given an angle BAC to start with, can we find points D and E between B and C such that angle BAD is equal to angle DAE, which is also equal to the angle EAC. Can we cut an angle, in other words, into three equally sized pieces? Euclid showed you could cut an angle into two equally sized pieces, but is it possible, just using the postulates and the common notions, to cut an angle into three? Not piece, but three equally sized pieces. So that's the first constructability question, something that geometers for thousands of years were trying to figure out ways to do. The second construction is going to be about doubling a cube. And the question we have for doubling a cube is, given any cube to start with, let's say we know that the volume of this cube is equal to V, where V is just going to be some number, like 1 or 2 or 3 or 4, etc. Question is, given the cube, can we always find a way to construct a new cube whose volume is twice the volume of the original cube? In any cube, can we always construct a new cube whose volume is two times the volume of the original cube? A very similar sort of question to the one we just looked at the start of class today. Given a square, can we always find a way to make a new square whose area is double the original square? Turns out the answer to that question was yes, and Socrates had a way to do that. Or Plato had a way to do that and is attributing that way to Socrates. One of the two. In this case, though, we're basically asking the same question, but in 3 dimensions instead of 2 dimensions. Given a 3-dimensional cube, can we construct a new 3-dimensional cube whose volume is twice the volume of the original cube? Very related question, but much more difficult to answer. Geometers struggled with this one for thousands of years. And finally, the third question that the Greeks kind of were stuck on and weren't sure how to do, and geometers continue to be stuck on for thousands of years, how to do this with straight edge and compass, is the question of how can you square a circle? Which basically asks the question of, if we have a square where the area of that square is some number a, can we always construct a circle with the same area? Given any square can we construct a circle whose area is the same as the squares? Meaning, can we basically take any square and just shift it around a little bit, play with it, and massage it into a circle that contains the same amount of area inside of it as what the square has? So you might be wondering to yourself, Dr. Bristol, we haven't talked about the areas very much in this class, or volume. What do these things mean? Euclid had terms that he used to define things like volume and area. We're not going to get into them in this class just because, for lack of time. Use your intuition, I think, for now to say what does it mean to have areas or volumes. It means the same things that you probably are intuitively thinking of. Euclid had terms to define them which are interesting, but we're not going to really get into those in this class. And so, you might be probably wondering, Dr. Bristol, are any of these things possible? Are all of these possible using tools from Euclid's Elements, from using Euclid's original postulates? And it turns out the answer to all three of these is the same, which you might guess from the title of the packet, Constructability Failures. The answer is no. You cannot, I repeat, cannot do any of these constructions using a straight edge and compass, meaning using Euclid's postulates and common motion. While it's always possible to bisect an angle, it's not always possible to trisect an angle. While it's always possible to double a square, it's not always possible to double a cube. And then you can't, in general, square circles. And so I think that's where, let's see, what's our time? 33 minutes. Yeah, I'll cut it off about there. That's where we're going to leave things off for today. In the next class, we'll finish off Standard 17 and talk about a little bit about why can we not do any of these three constructions in general. Answering a question that it took geometers thousands of years to answer that you couldn't. This is something that was definitively answered in the 1800s. Why is it not possible to square a circle or to double a cube, even though we could say double a square? Hope you all are doing all right. I'm going to post this video on YouTube now, and I will see you all in the next one. Joke of the day. I think I forgot to joke of the day. I just realized it. What do mathematicians wear to keep the sun out of their eyes? Keep the sun out of their eyes, mathematicians will wear the visor. All right, have a good one.